So first of all, you need to know that the Earth is around 4,500 million years old. So that's a very difficult number to get hold of, right? So what we try to do in the deep time walk is get a felt physical understanding and sense of how ancient our Earth is. And if we do that, we hope that our respect for the Earth will increase through this terrible crisis that the Western culture has caused and wreaked upon her. That we can, in our lives, do something to help improve the situation. I think before we can really do anything like that, we need to really have a strong feeling for the Earth. So we're going to walk actually 4,600 million years, that over a distance of 4.6 kilometers. So 4.6 kilometers represents 4,600 million years. And on that scale, every meter we walk, that's 1 million years. And on the same scale, every footstep, that's 500,000 years. So let's say we're 4,500 million years ago here. There was no Earth. There was no solar system. But there was a big star. And that star exploded into a supernova. And in that explosion, a whole lot of heavy elements were created. Carbon, nitrogen, sulfur, all the elements of the periodic table, they were all created. And they started swirling around. So it's a huge explosion, the supernova explosion. And in one little bit of it, some of that dust, let's call it dust, of these elements started swirling around. And in the middle, there was a clump of hydrogen that ignited to form the sun. This same sun we have now. And that dust around the sun started swirling and swirling and swirling. And little grains of matter started forming, and little grains of matter started clumping together until we end up with the planets. And by the time we get to here, 4,500 million years ago, the Earth has formed. But it's nothing like this, today's Earth. The thing is, it was a molten ball of rock. And now look at all this. You know, trees, blue sky, 20% oxygen, humans, birds, rainforests, coral reefs. All started off from a molten ball of rock. How is that possible? How is it possible? Well, we don't know. In science, we have no idea. So let's keep walking. We'll go towards the present day. Every millimeter is 1,000 years. And let's just walk in silence for a few hundred million years. So just so you get the feeling of it, okay? It's this Earth. You have to do two things. You have to put yourself in the past and also remember the Earth now and compare those two states. Yeah, it's not easy, but it's sort of like a practice. Okay, let's go. You see, we think there were two planets in the orbit of the Earth. One size of the Earth and the other size of Mars. Both molten balls of rock. Can you imagine them? They're going around the same orbit. And then eventually, there's a huge collision. I mean, immense. And the two of them kind of melt into each other. And there's an incredible mixing up, exchange. And then some of that molten rock, with the sort of the momentum of the impact, it spins out into space and forms lots of little molten droplets. And they themselves then sort of feel attraction for each other and they coalesce into another planet. Guess which planet that is? Still there today. Very close to us. Any idea which that planet is? The moon, yeah. The moon. And this is really important for the future of life, because if we hadn't had the moon, we wouldn't have a stable axis. The axial tilt of the Earth wouldn't be stable. So imagine I have a magic string here and I attach it to the moon. And I fling the moon way out into space right now, okay? What will happen is, slowly, the axial tilt of the Earth, which is around sort of 22 degrees at the moment, it'll start moving around unpredictably, chaotically. And that means we won't have predictable seasons. And therefore complex beings like us, multicellular beings like us and the trees, wouldn't survive. We'd probably have bacteria, but we wouldn't have us. So now we bring the moon back, put her back in her place. And she stabilizes the axial tilt of the Earth. I mean, it does wobble a little bit, but not much. And that means we have predictable seasons. Now the chances of getting an impact that gives you a moon are very, very small. Most of the impacts that scientists have modelled on computers don't give you a moon. They give you one large planet, two equal sized planets, lots of sort of dust in space. It's very, very hard to get a moon. But because we have that moon, we are here. Isn't that amazing?
Yeah.
It's a very deep philosophical question, isn't it? Now, by the time we get to here, about 500 million years after the formation of the Earth, from the supernova explosion by the road, remember? And we got to here. The crust is the molten surface of the Earth is starting to form a crust, so it's cooling and forming a crust, a rocky crust. But it's still dry as a bone until the water arrives. And around about now, the water arrives. And there's two ways we think the water arrived. One is more poetic, and probably wrong. And one is scientific and less poetic, probably right. The probably wrong poetic one is that some massive lumps of ice from the asteroid belt. Jupiter and Saturn were a bit closer to the sun, I think, and they moved. These huge lumps of ice came hurtling towards the inner rocky planets. Anyway, so the lumps of ice crash into the 5 or 6 lumps of ice. That's enough. That's all it would. So you get the picture. Now we have an ocean planet. It's very cool at the moment. Isn't that remarkable? Footstep, 500,000 years. We'll do some more quiet walking later on as well. So this is around 3,500 million years ago. And during all the time we've been walking up to here, the water has been dissolving chemicals out of the rocks. And those chemicals have been saying to each other, hey, look at this. This is a nice place. Look at this. It's very rare to get a place like this. It's liquid water. It's just the right temperature. Why don't let's try getting together and different stuff. In other words, this organism, which was something like a bacterium, but before the bacteria, probably, it was the ancestor of all living beings. We know that because we all share the same DNA, the same genetic code. So it must have come from one original ancestor. And eventually the bacteria evolved out of that. So now we've just got a bacterial biosphere. But the bacteria aren't everywhere. They can only live around places where there's chemical energy coming from the rocks, mostly around volcanoes. Then they can't spread any further. And so, bacteria are incredibly creative. So it's nothing, apart from the appearance of life, nothing much has changed. It's oceans, volcanic islands, CO2 atmosphere, no breathable oxygen. Isn't it amazing to think, look at her now, these massive trees colonizing, and we've even got continents, first of all. That's a miracle in itself, that we've got continents. Where did they come from? And then, look, the continents are covered with life. But of course, all this is going to happen in the last 600 meters. All right, ready? So let's keep walking, keep the meditation going. All right, so this is around 3,000 million years ago, more or less, when it happened. One little bacterium, just one, invented the art of using sunlight to split water. It's an incredibly difficult thing to do, almost impossible, because this bacterium had to integrate 2 separate photosynthetic pathways from the old photosynthesis and invent a new sort of aspect of photosynthesis called the water splitting complex. And to do all of that, very, very difficult, but it did it. Now the thing about bacteria is that they engage in something called horizontal gene transfer, which means they can take a little bit of their DNA and make copies of it and then share it with other bacteria in their surrounding and those bacteria can then express that trait. Now, Lynn Margulis, who's one of the great biologists who studied all this, who was also taught at Schumacher College, she has a nice way of explaining this so you can understand it. And in a few 100 million years, that ability of oxygenic, we call it, oxygen producing photosynthesis, water splitting photosynthesis, was all over the surface of the ocean. All the billions and billions and billions of bacteria. It spread like wildfire all over the surface ocean. There's plenty of carbon dioxide in the atmosphere, there's plenty of water. So, what's this going to have? Sorry, what impact is this going to have on the climate of the Earth? Now we've got huge numbers of bacteria all over the global ocean extracting carbon dioxide from the atmosphere. So you've got three choices. Go on, yeah? The oxygen in the air, yeah. They're going to be producing oxygen, yeah. But the oxygen doesn't actually affect the climate.
They're cooling it down?
Yeah, why?
Because, why?
Yeah, you're right, they're cooling it down, but why?
Because CO2 traps the heat from the sun.
Yeah, go on. And why CO2? That's right, yeah. CO2 is a greenhouse gas, right?
Yeah.
So what's the reaction that's going on in photosynthesis?
If they're splitting the water and they're putting oxygen in the air, so there's like just a different proportion of oxygen to carbon.
Oxygen, a greenhouse gas has to have 3 or more atoms in it. So O2 has 2 atoms, so it's not a greenhouse gas, right? So what's happening? You've got to know this as growers, okay? Because you're growing plants, right? So why do plants grow? What are they doing? Where do they get their energy from? Synthetic bacteria sank to the bottom of the ocean. There are other bacteria that like to decompose those dead bodies. We call them fermenting bacteria, right? They like to decompose those dead bodies. And they release methane, which is a greenhouse gas, and carbon dioxide into the water, and it bubbles up into the atmosphere, and that stops the Earth from freezing. So you've got one kind of bacterial ecosystem on the surface cooling the planet by removing CO2, like you said, through water splitting photosynthesis. And there's another bacterial ecosystem in the sediments at the bottom of the ocean that's decomposing the dead bodies of the photosynthetic bacteria and releasing carbon that's in their bodies back to the atmosphere in the form of methane and carbon dioxide, both of which are greenhouse gases, which prevent the Earth from freezing over. You get the idea that one ecosystem on the surface is cooling, the other one in the sediments is warming. So you get a cooling and a warming, you get these two opposite dynamics. This is Gaia. So we should have another glass of champagne. To the birth of Gaia. Gaia. It's just a bacterial Gaia. All right, let's keep going. A few more 100 million years, then the next thing's going to happen. It's about 2,500 million years ago. Still 1% oxygen. There's plate tectonics kicking in, so now we're getting some reasonably large continents. Nothing like today's continents, but they're barren. There's no life on them. But in the ocean, something remarkable has happened in the bacterial realm. So let's make a bacterium, let's make a circle. I wouldn't recommend we hold hands because of COVID. Let's close the circle, I'll be in the middle. So you're a bacterial cell, okay? I'm inside the cell, you're the membrane. And we're a predator, we're a predatory cell. So we're able to engulf other bacteria and digest them, right? Now let's see, would you mind stepping outside? What's your name? Blue. Oh, that's nice, Blue. So Blue, she's a very special kind of bacterium because Blue can use oxygen to break down food molecules. We can't do that. We have to use a more old-fashioned kind of fermentation system, which is pretty inefficient. But Blue is really good at digesting oxygen, you see. That's why she's blue for some reason. And also, Blue's kind of bacterium, very nice to eat. We've eaten lots of them before, so we're gonna engulf her, and we're gonna start digesting. But I'm her lawyer, and I'm Blue's lawyer, and Blue has a proposal to make, which is don't digest her, okay? Let her stay in here, and in exchange, when you want some food, instead of you trying to digest it with your very inefficient, let's face it, it's very inefficient, your fermentation, it's really very inefficient. You give her the food molecules, and she'll use oxygen, which diffuses through you, through the cell membrane, to digest the oxygen, and you can get so much energy, and you can get bigger. You can have a huge nucleus in here with much more DNA, you can become more conscious, more aware, you can do more things, more creative. The same thing happens with cells that are with bacteria that are photosynthesizing. So we'll take in a. Would you mind stepping outside because you're nice and green? You see, she's a lovely photosynthetic bacterium. Look at her, all green, really lovely, making sugars. She's really nice to eat, like a chocolate. She's so lots of sugar. So we bring much further down the track. No, you need to stay. No, you need to stay. Now we've got a new kind of eukaryotic cell, right? Like the plants. So what happens with the plants is the photosynthetic bacterium becomes the chloroplast in the plants. You should know about chloroplasts since you're all growers, right? They were once free-living bacteria, basically, and they do the photosynthesis. They produce the sugars and the oxygen. Now, when you want some energy, you don't even have to eat anymore. You just say to our chloroplast here, could you make some sugars, please, for photosynthesis? The sugars go to the mitochondria, and the mitochondria burn up the sugars, and you get the energy. Right? That's where our energy comes from. And all the other organisms can then start eating. This is good, yeah. I should start as well.
They escape.
And they're trying to escape the floods. This is the whole
Update. Nothing much has changed.
Thank you.
540 million years ago. Just up as we were coming up the path, we had a few periods of what we call snowball Earth, when the Earth froze over completely. And for complicated reasons I'm not going to go into now, that did two things. One is it raised the oxygen concentration of the atmosphere, these snowball Earths and the recovery from the snowball Earths. And then also it might have forced the single-celled organisms to become multicellular. So by the time we get to here, this is the famous Cambrian explosion. Have you heard about that? Where if you look in the fossil record around 540 million years ago or so, you get lots of multicellular organisms. Things like sponges, the first sort of worms, the first, have you heard of trilobites? No, trilobites. Well, Julia, one day, my wife, did you know Julia's my wife, who cooks the food? One day she will cook you a trilobite, but she calls it a spinach plat. So look out for the spinach plat, it looks like a trilobite. So we've got mollusks, the ones that will be eating your vegetables. Snail, very early forms of snail. We've got worms, I mentioned. So, and the oxygen is around 10%. So do you see it's just a really rapid shift from where we were down there by the river, which is mostly unicellular organisms of two kinds, and suddenly around here the eukaryotes, boom, they become multicellular. And we think it's partly because the oxygen went up to 10% for various complicated reasons. And that meant there was enough free oxygen for multicellular life to really take off. So, from now on, things are going to change really fast, okay? It's the last 600 million years or so. So let's stick together, although not too close to me for COVID reasons, and then we'll see what happens. We will, of course, in the end, get to 2022, we hope, unless we get lost in deep time. That would be serious, wouldn't it? What would we tell the college? We've got lost in deep time.
timeline. You know where?
Yeah, it's like, it was like
480 million years ago. And at last we're getting the first land plants. But they're very primitive. They're these mosses. You see the mosses here. They don't have any roots. They have sort of little extensions that go into the rock, I suppose. And they may be pairing up with fungi, you know. And they're extracting nutrients from the rocks, and they're making the first very primitive soils. So this is the moment for you growers, you know. 480 million years ago, first very, very primitive plants. Although that's an insult to call them primitive, because it's an amazing achievement. There are any plants at all, considering you have to shift from a single-celled eukaryote to a moss. That's an amazing achievement, isn't it? So I hope they're not crossing me calling them primitive. Apologies. You could say they're primitive in the sense of very early, that's all right. Then we get the first fish in the ocean. But they don't have any jaws, so they can't talk. They have jawless fish. I think that's all we need to know. The trilobites, well, you don't know what trilobites are, but they're diversifying. I might bring some little pictures in future to show what trilobites are like. 443 million years ago, more or less. And the earth gets warm. And those mosses that we had just along the edges of the continents, they're now growing along streams. You know, they're starting to grow into the continents. Can you imagine that? And we also get the first vascular plants. You know what I mean by a vascular plant? A plant with internal tubes. Mosses don't have internal tubes, but the plants you're going to grow, they all have internal tubes, don't they? So we get the development of internal tubes in plants. That's pretty amazing. They maybe have very shallow roots, but no proper roots. I'm pretty sure the fungi were associated with their roots, very primitive roots, and helping them. Of course you know about the mycorrhizal thing, don't you? No? Yeah, good. Okay. It's really important for growers to know about that. About the importance of the fungi and roots. And we're also getting now the first terrestrial animals. They've crawled out of the sea and they've turned into millipedes and little spiders. Is that amazing? You know, there's those sort of animals we were talking about in the sea. They've now become spiders and millipedes. Okay, let's keep going. We're in the lower Devonian now. Some of the rocks not far from here are from this period, 400 million years ago. Now we've got forests of plants with tubes and roots covering nearly all the continents. Can you imagine just since we last stopped, all that evolution that's happened? And they don't have flowers though. They're spore-making plants. And we get the first really decent leaves and the first proper seeds and the first really stable soils at last. And the climate starts to cool as these plants start drawing CO2 out of the atmosphere. And we also get the first insects. Some of them have wings on the land. And they join a thriving community of mites and scorpions and millipedes and spiders and lots of other animals without backbones. There are no animals with backbones on land, they're all in the sea. And at last, the fish have developed jaws. So they say to themselves, hey, what do you think, guys? Shall we colonize the land? Some of them might poke their heads out of the water and see all those juicy millipedes crawling on and think, yes, let's colonize the land. I'm being very anthropomorphic.
So when the cells are put using fermentation.
This is the upper Devonian, when there were lots of coral reefs all over the place, especially here in Britain, which was in the tropics in those days. Wouldn't that have been nice? So, we've got forests everywhere now, but there's a problem. because the plants have now developed wood. They've invented wood. These are actually ginkgo trees, are some of the earliest trees. I'm not sure of the age of the ginkgo, I have to look it up. Anyway, we get the first proper wood, and this woody plant spread all over the planet, and this is a major danger. Can you think why? Why is this a major danger? Sorry? To life. Why is it a danger to life? Why could widespread wood be a massive danger to life? Not fires, although fires, yeah, but that's not the main reason. So the coal that we have from all over the planet, we're burning and destroying our climate with, that comes from this time, from the trees that fell into swamps and weren't decayed. Let's see, yes, and we get, but of course, as you mentioned, there's one kind of organism that finally discovers how to decompose the wood. Thank goodness, otherwise we wouldn't be here. Which organism was it? You've got a choice. Was it the millipedes? Was it the spiders? Was it the fish? Was it the amphibians? Was it the bacteria? Sure?
Yeah.
Sure? Not the bacteria. It was the fungi. The fungi, they set their tune. Now, one thing about fungi, when I was taught by a great fungal ecologist, he said to me, if you write about fungi, I never want to see you use the phrase fungal thread. I said, okay, he said, always say tubes. So they don't have threads because threads are solid, right? Fungi are made out of tubes, and that's how they can live. The tubes are full of enzymes that, in this case, went into the wood, and they discovered how to digest wood. It's amazing. If you give a wood-rotting fungus some food, guess what? The best food you can give a wood-rotting fungus is. It's remarkable. A block of wood. A block of wood, which to us seems sort of it is utterly indigestible. To a wood-rotting fungus, it's delicious. A block of wood, can you imagine? They send their tubes into it, and they start sending enzymes into the wood, and they suck up all the nutrients in the wood, and they release carbon dioxide to the atmosphere. And that's what stopped the Earth from freezing over. So, we're learning more and more about the importance of fungi for Gaia. So we could live now in this. If we landed up in the Carboniferous, we could live. We could breathe the air, be very comfortable. We've also got the first primitive reptiles. So some of the amphibians are becoming more detached from the land, and they're turning into reptiles. In terms of plate tectonics, the continents are now coming together. Remember, they're all covered in vegetation now. They're coming together to form the last great supercontinent called Pangaea. Okay, let's keep going. When the supercontinent Pangaea has already has formed, and it straddles the globe from north to south, a massive supercontinent. Can you picture it? But the inside of the continent is very dry, so you get a massive desert in the inside of the continent. And the fact that the supercontinents come together has created so much volcanic activity that we get a mass extinction because of that. Things go very warm, very hot. A little bit later, about 250 million years ago, around about now, because of the supercontinent, things get really, really hot. It goes up to about 4 or 5 degrees previous to the supercontinent, and it's an absolute disaster. I mean, you get the biggest mass extinction of all time happens. Just think what that means for us if we warm up our planet now by 4 degrees centigrade relative to pre-industrial times. If it's anything like the Permian, we're going to have a massive, huge mass extinction. But anyway, the reptiles do very well in the dry climates. We get diversification of reptiles. Some become really huge herbivores. Some become carnivores. Yes. Well, there we are. You see, we have to learn from the Permian mass extinction. There were probably huge releases of carbon dioxide from the volcanic activity, equivalent to our releases of carbon dioxide. So remember, the Permian mass extinction, huge mass extinction. 4 to 5 degrees of warming. We're going the same way. Of course, we don't have a supercontinent now, but impacts could be similar. Okay, let's keep going.
Yeah, I did. Oh, I know.
The paradigm's slowly shifting from a totally mechanistic one to a more, I wouldn't say animistic, but sort of quasi-animistic, you know. So, here we are. We're around 200 million years ago now, and we've got the age of reptiles. You get the first flying reptiles, the pterosaurs, and the first dinosaurs, but they don't become dominant for another 50 million years. It's only 50 meters. And we also get the first true mammals, our direct ancestors. The first mammals appear. And we've still got amphibians, of course. Some of them are very large.
Thinking about it. It was big all the time. Obviously.
Alright, so this is around 180 million years ago. It's just to say that the continents are now really splitting apart. And we begin to discern the shapes of North America and South America and Australia. You know, they're in different places, but you can recognize the shapes. Okay, keep going. Alright, so this is around 136 million years ago when the continents burst into colour because we get the first flowering plants. And that's because of a symbiosis between the plants and the insects. But up until now, all the pollination has been wind pollination. Now, this new symbiosis has appeared in which the plants produce these gorgeous flowers, look at them, with colour and nectar, which the insects find irresistible, and so they start pollinating the plants. And we get this wonderful symbiosis. It's very successful, spreading all over the planet. All over the planet, we get colour, beautiful colour, due to this symbiosis. On the other side of the Earth, of course, massive volcanic activity released huge amounts of carbon dioxide to the atmosphere and warmed up the planet. And also the impact is probably on some carbon-rich deposits. So you've got loads of CO2, lots of warming. And we got massive clouds that actually blocked out the sun, so we had short-term cooling and long-term warming, and basically this wiped out nearly all the dinosaurs, apart from
Chickens.
chickens.
Yes!
Well, actually the ancestors of the chickens. Yeah. All the birds are dinosaurs.
Yeah.
So there's beautiful little birds like the chiff-chaff that we just heard calling, the great tits and the blue tits and the robins, and they're dinosaurs. Very sophisticated dinosaurs. But all the big hefty ones disappeared. Last 300,000 years. So our species arrives somewhere between here and here, 300 to 200,000 years ago. Us, Homo sapiens, just like us. People exactly the same as us. Not psychologically, but physically. Psychologically, they're much more connected to the whole of Gaia, unlike us. Then we get various ice ages. Let's go, relevant to you growers, let's go to 8,000 years ago, when we get the farming revolution. That's 8 millimeters, that's about here. I should really put it like that, you see, sorry about that. There, like that. 8 millimeters, that's the farming revolution. Can you get an idea for 8 millimeters? Maybe I should use a stick here, just to point to it. So 8 millimeters is about here. So about there, just imagine how far we've walked. So we're like that, right? But we had Buddha a little bit earlier. But let's say these great sages, Buddha and Jesus, roughly at the same time, 2,000 years ago. That's only 2 millimeters. I mean, 2 millimeters. Can you get the idea? So 2 millimeters, like that. And then, let's go to the Industrial Revolution. which has messed up the planet, or started to mess up the planet, big time. That was, how long ago? Say 500, 400 years, 200 years ago. That's 1/5 of a millimeter. I can't even show you 1/5 of a millimeter. You know, I can't even show you can see a millimeter, right? That's 1/5 of a millimeter. That's when we started destroying the planet. We have to put it like this. I should really be standing here, so you can see it along the walk. See what I mean? 1/5 of a millimeter. Dangerous time Gaia has ever faced, and it's entirely due to Western. I don't want to say Western because then it plays into sort of anti-Western sentiment, to modernity, to consumerism, modernity. So welcome to the present moment. Now before we disperse, let's take a few moments just to really allow what we've just done to sink in, to allow the depth of time that we've walked to really sink in. And also, we might want to make a pledge inwardly to do something with our lives to help to improve the situation. So let's just do that for a few minutes, a few moments. Because I know you're going to make some sort of big difference when you go out in the world, and you're part of thousands of people who've been to the college over the last 30 years, many of whom are doing really big things, some of them are doing small things, but everyone's doing something. So welcome to, well, you've already been welcomed, but we're now part of the Schumacher Gaia family, you could say. So thanks a lot. Hope you got some rich learning.